Yeah? Have you been
Not yet.
introduced? Not yet. Okay, never mind. So that is so Emil Post worked on many interesting problems in related to computing. So we will look at one of his work over here in flat. You'll very likely look at another of his work. So the work that we are seeing here is on functional completeness of Boolean functions. So his treatment on functional completeness of Boolean functions is based around 5 classes of functions. So these are fairly simple classes. So first class of functions is those are called truth preserving functions, or T, you can just call them T preserving functions. And the requirement is expressed over there. That means, so if you have a function of n places, okay, so for a function to be T preserving, just this requirement needs to be satisfied. That means when all the inputs are let's say T, that is true, then the output should also be true. So that's called a T preserving function.
Yeah, we can see you. We can see the slides.
Hello?
Yeah, we can hear you.
Okay, I think I got muted.
In between,
somehow.
you got muted.
Huh?
In for the 2 minutes, you got muted.
Okay.
So when you are sharing the slides, you got muted.
Oh, so how much?
No, we did not miss anything. We did not miss anything.
All right, but can you see the slides?
Yes.
All right, okay. Yeah, so I talked about F preserving functions. That's where I stopped. So did you hear about F preserving function? Yeah?
Yes,
Hello?
we did.
Okay, all right. So, okay, so those are, so for a function to be F preserving, um, for a function to be F preserving, you just need to satisfy that requirement that, so if all the inputs are F, then the output is also F. All right. Now, for so you also have counting functions. Now, these counting functions are very interesting. So, a counting function is simply a function where all inputs matter. That means if you change any input, there should be a change in the output. All right. So when it comes to when it comes to counting functions, we also uh, classify the variables as dummy or non-dummy. So, I mean, the concept of a dummy variable is quite straightforward. I mean, suppose you have a function of say 2 places. Now suppose you want to extend that function to be of 3 places. All right. So you can introduce a dummy variable, and the role of the dummy variable is only to increase the number of places. It doesn't have any effect on the output. So to just define the role of a dummy variable, we can say write it like this. So suppose you have a function x1, x2, x3. Now suppose let us say this position, I'm just writing, suppose this position is a dummy position. Suppose x1 is a dummy variable. So what is the property of a dummy variable? So dummy variable is for all x2, x3, if x1 so in other words, you can say that it has no effect on the output of the function. Alright, so that is what a dummy variable is. Alright, so I think so I hope the role of a dummy variable is clear to everyone. Anyone has a doubt on the role of a dummy variable? Is it okay? Alright, so now what you're saying is, if you have so if f is a, so now we say that so for a counting function, if it's a counting function, then we say that, so this is your f. So if we, you might have some dummy variables, let us say x1, x2 and so on, and then let us say you have non-dummy variables. So for a non-dummy variable, f, so these are your so in other words, any change in the value of any non-dummy variable is reflected at the output. Of a counting function. And this class is referred to as the L class. All right. So this class is referred to as the L class. So, are you okay with the definition of counting functions? Yeah. Any questions regarding the definition of a counting function?
So what is the difference between a normal function and a counting function?
Okay, very simple. Consider the AND gate. Consider the AND function. Would you call
Yes.
it a counting function? Let us see. So, if you let us
Okay,
consider
because for 0, 0 and 0, 1, it's giving 0 only, so it's not
if
a counting function.
so f00 is equal to f01. All right,
Okay, so it's not a counting.
but that is not enough. What you need to show is that this is not a dummy function. Non-dummy. So how do you show that it is a non-dummy? So you can show it like this: f10 is not equal to f11. All right. So rather, I should just put it this way. This establishes that it is not a dummy function. This is not a dummy position. All right. So this is for a non-dummy position. For a non-dummy position, it should make a difference, but it is not making a difference. So,
Oh,
okay. So this is a non-dummy position, as you can see. So this is not counting,
mm,
not a counting function. All right.
yes, sir.
All right. Any other questions? All right. So that is about,
Sir,
yeah. Someone wants to say something?
sir,
Or
so in order to prove that a function is counting, we would have to take like every possible values of the other variables.
we will actually, there is a very, yeah. So that's a good question actually. How do you know that a function is a counting function or not a counting function? So there is a good test for that. So okay, so let us look at that. It's a good question. So let us look at that. So what you see is that, so if you consider a row, you consider the rows in the truth table of the function. Okay, sorry. you consider, okay. Let us consider the truth table of the function. So this is what a truth table usually looks like. You have, x1. So let us just consider non-domain variables, x2 and so on, xn. All right. So you have some variable. Okay, let us say 0. Let us say, you have some variable, some value. I'm just taking some arbitrary values. 1, 1, 0, 0, 1. Okay. Output may be 1 or 0, whatever. Let it be anything. Let us say that this is a row. Now, let me just change any value. All right, let me just change any value. So, let us change this value here. So, I am going to get this, this, this. And it's a counting function, so output must change, right? So let me change any value. Let me now change this value. You can change any value. Let us say this. Let us change this one. So this one, sorry. So output must change. Now let us change any other value here. So let us change this value. Output must change, right? So from this, can you make any observation? Can you make any observation from the discussion that we just had? Can you make any observation?
It would be alternating.
Just so what observation can you make? Actually, you have come across such functions already. You have dealt with such functions already. And if you want a further hint, let me point out to the exercise that you did on error correcting codes. So there you dealt with such functions extensively. So can you say something about such functions? Huh? We just had a discussion on how the effect of the so-called counting nature of these functions. So from
So
this,
it is like
Cyclic functions.
yeah, can you come again, please? Hello.
Sir, these are the codes that differ by just 1 bit.
No. You can change any value. Yeah, of course. Okay, we're changing one value at a time, but in the truth table you will have all the rows, right? You will have all the rows. So can't you see that the parity of ones do you see this? Yes?
Yes, sir.
The parity. So you have a test. So all you got to check is that all the rows have the same parity. Okay. All the rows have the same parity. All right. Sorry. All the rows have the same parity. So that is a test for this dummy function, test for this dummy functions. Test for this counting functions. So if you want to check that a function is a counting function, then that is a good
Sir,
check.
but this still means that we have to check for every possible input combination, right?
Oh yeah. You'll have to check. Yeah, that is a check on the truth table. But that is that's
So,
a check.
Sharon, is it true that if we delete the columns of the dummy variables, and
So dummy variables have no effect, because when we check or when we look at a counting function, we always disregard the dummy positions anyway. So that is like deleting only.
okay,
Yeah, so we disregard the dummy positions. When we look at a counting function, we disregard the dummy positions. So in this particular case, I mean, we assume that all of these are non-dummy positions. These are all non-dummy variables. Okay. Is that okay? Any other questions regarding counting functions? I mean, hello? All right. Then let us carry on. So next we have monotonic functions. So monotonic functions, you are all, I mean, you all have the notion of a monotonic function. So let us just define it. So for monotonic functions, first of all, let us, so you have got two values, say T and F, alright, T and F. So you have seen that in a Boolean lattice, for example, if you have a two-element Boolean lattice, then you have just two values, right? If you have a two-element Boolean lattice, then you will have just two values. One will be false, one will be true, or if you like, one will be 0, one will be 1, and the other will be 0. I mean, so we have this ordering that 2 is less than or false is less than or, all right, and you have, so if you have an input vector, so if you call it x, you call it x1, x2, x1, x2, etc., xn, and if you have you know, y as y1, y2, yn, then x is less than or equal to y if and only if x1 is less than or equal to y1 and x2 is less than or equal to y2, so on. All right, so that is the definition of, you know, how you can compare. So, you know, when you can say that a vector of inputs is less. So if you have, so now if you have, you know, if you have a function f, so you say that f is monotonic if 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 x less than or equal to y implies, or maybe if I just write it over here, function f is monotonic if x fx is less than or equal to. Okay, so this is the standard definition of monotonicity. All right, this is the standard definition of monotonicity. So now again, can you give an interpretation of monotonicity with respect to Boolean lattices? So if you think of a lattice, for example, so you had, I think, a diagram like this. Sorry. Maybe you can just draw it a little better. So this is the bottom element and this is the top element. So what you're saying is that so some of these elements will be 1. So when you choose your 1 elements, so suppose this is 1. So you can choose your 1 elements. For example, would you say that this lattice, if you think of this, so here, I mean, these are the inputs. This is the ordering of inputs. If you just consider the inputs, so this is we can say 0 0 0, then this is your, let us say, 0 0 1, this is 0 1 0, this is 1 0 1, this is 1 1 1, this is 0 1 1, this one is oh sorry, this one should be, yeah, this one should be 1 0 1, this one should be, this is 1 1 0. So these are your inputs. All right, this is the so your Boolean function, I mean, I'm just highlighting the input, the nodes that are 1. So this is your the lattice of your input vectors only. This is the lattice of your input vectors. So basically, if you think of coloring the nodes from the top, so if you want your function to be monotonic, you can color your function from the top. Now I'm just saying, suppose if you make this, then it will not be monotonic if you keep this one, because this particular node is 0, this is 1, so it breaks the monotonicity. So if you want it to be monotonic, then you should either drop that or you should keep this also, like that. So if you think of, you know, the inputs that come. So if you create a lattice of the inputs, so that I mean, that is graphically how you can visualize monotonicity. That means the upper nodes, you should not, if you paint, so you can say that you can say that you're painting some nodes as, all right. So when you're painting some nodes as T, I mean, you got to start from the top and come down. If you have gaps in between, then your lattice will not be monotonic. It will break the monotonicity. All right. So that is the idea of monotonicity. Okay. Yeah. So I hope you understand this. The monotonic property of or the property of this monotonic classes of functions. Is that okay? Any questions there? All right. Okay. So let us look at the self-dual function. So self-dual functions have a simple definition over here. You know, it is just, it's given over here. It's a very simple definition. Self-dual function. This is the definition of self-dual functions. So if you complement the inputs, the output should also be complemented. That is the property of a self-dual function. All right. That is the property of a self-dual function. So these are the 5 classes which have been considered by Post. And then you have the statement of the theorem. All right. You have the statement of the theorem. That is a set F of Boolean connectives. These connectives are functions. For example, you say and, or, these are connectives. These are also functions. So a set of Boolean connectives is functionally complete if and only if for each of the 5 defined classes there is a member of F which does not belong to that class. All right. So you must have a member of F that doesn't belong to that class. So I mean, to understand this easily, because you can always, you know, carry out a simple, you can check on a simple example. So you already know, you are already familiar with certain functions, just single functions that are functionally complete, right? For example, the NAND function. All right, the NAND function. It's also called. It is also denoted by, you know, this. So this is. Okay, so these are some, you know, representations of NAND and NOR functions. So you can just check for yourself. You take any one of these, NAND or NOR, you check whether it passes any of these tests. So all you got to do is you test it for, whether it belongs to the class T, whether it belongs to the class F, L, M, S. So you'll find that, NAND actually it fails on all the classes. That means it is not a member of any of these classes, and that is what makes it functionally complete. Same is true for NOR, but please check it out for yourself. Can you check it out for yourself? Yes? Hello? Both these functions, can you check out these functions for yourself, that these are these do not belong to any of these classes? Are you with me?
Yes, sir.
Yeah, so what I want you to do is, of course, T and F, these are very easy. So can you identify inputs to NAND and NOR? You just consider two place NAND and two place NOR functions, which will allow you to prove that these functions do not belong to this class. I mean, obviously it doesn't belong to true, because you know that is zeros, and you know that so like that. Can you give some inputs which prove that it's not part of, it doesn't belong to L, it doesn't belong to M, it doesn't belong to S? All right, so of course actually, huh?
So we did the case of AND function. So similarly would be for NAND.
Oh, no. And does not satisfy, because and satisfies this.
No, sir. I'm just saying that we just proved that and was not a counting function.
Not a?
Not a counting function.
Yeah, okay. So that same proof will allow you to, do for, yeah, but what about the other classes? You can check for the other classes. I mean, actually, these two inputs, these for NAND, these two inputs show that it's not monotonic, right?
Yes, sir.
Isn't it?
Yes, sir.
Yes, sir.
So can you, but these two inputs, do they prove that NAND is not self-dual, these two inputs?
No, sir.
Then can you identify inputs which prove that it is
0, 1 and 1, 0.
Yes, sir. 1001.
1, 0? This is equal, right?
Equal to its complement.
So it's not a self-dual. So that way. Similarly for NOR, okay. All right. Probably I should remove this. This might create confusion, so I'll just remove this. Yeah. So, okay. All right. So, yeah. So that's an interesting test, Now, if you consider AND and OR, okay. If you consider the the set and or I mean, there are many ways to write the complement. Sometimes you write it like this, sometimes you write it like this. All right. So what about this set? Can you test out for this set? Is this set functionally complete? Can you apply this test? Can you apply this test, posts test on this set? Just here. Can you test this out and tell me? What can you say about this set? Yeah, can you test it out and tell me?
Yes, sir.
So which one belongs to which set and which one doesn't belong to which set? Say and. Let us take up and. Does and belong to this class T?
Yes,
Yes, sir, it does.
It does. Then you would expect that complementation shouldn't belong to class T.
Yeah, it
In
doesn't.
fact, it doesn't, right?
Yeah.
Yeah?
Yes, sir. Complementation doesn't follow T
Complementation
and F.
doesn't belong to T, it doesn't belong to F. But and does belong to T and it also belongs to F. So what about the other classes?
And doesn't belong to counting function.
So does not belong to counting.
Yes, sir, it does.
Yes, sir.
It does.
Yes,
So then you can take up monotonic. Is and monotonic?
No, sir.
Why do you say that it is not monotonic? Can you give a set
Yes,
of
sir, it is
inputs?
monotone.
It is monotonic. Complementation is not monotonic.
Complementation
Yes,
is
sir.
monotonic. What about self-dual?
And is not subdual.
Yeah, but not is self-dual.
Yes, sir.
Yes,
Not
sir.
as not as self-dual. But you do find that these two satisfy the requirement stated in Post's Post theorem, right? Together they satisfy. Individually they don't, but together they satisfy. All right. So just read the statement once again. A set of Boolean connectives is functionally complete if and only for each of the 5 defined classes there is a member of F which doesn't belong to that class. So for this set, this requirement is satisfied, isn't it? Yes?
Yes, sir.
So from that point of view, it is functionally complete. Now, so I mean, if you look at this table, so we have considered many functions. Now over here, of special interest actually are the first 2 columns, T and F. So T and F are also functions. All right. I mean, those are constant functions. So yeah, so you can see that T and F also they have certain properties, um, and so you have seen that the penultimate column XSY. XSY actually represents a multiplexer. S is the select input. All right. So you can, if you look at the table, I've just represented it compactly. So S is the select input. So what can you say about the completeness of this multiplexing of a multiplexer? You have seen that a multiplexer is functionally complete So is it functionally complete by itself? Yeah. My question to you is the multiplexer functionally complete by itself? Yes? What can you say? Look at the truth table, just look at the truth, this table and tell me. Is the multiplexer functionally complete by itself? You have done an experiment with using multiplexer. Huh?
Yes, sir, it's functionally complete
Now
by
you look
itself.
at the table. Multiplexer preserves T, it preserves F. So how can it be functionally complete? Yeah? It preserves T, isn't it? Is it T
Yes,
preserving?
yes.
And it is also F preserving. So how can it be functionally complete?
Sir, by
It is actually
including
not
both the
functionally
terms.
complete by itself, but it is functionally complete. So the set, the multiplexer along with the T and F functions, that is functionally complete. Because if you remember, you have to apply 1 and 0 also, isn't it, as inputs?
Oh,
Yes or
yes.
no? Yeah?
Yes, yes.
So the multiplexer by itself isn't functionally complete. It is functionally complete only when if you consider the set, that is F3, I have written here below, if you can see, F3, which has where is it? So if you look at this set, this is the multiplexer truth and T and F function. So T doesn't preserve F and F doesn't preserve T. Alright, so now if you take this whole set, then you find that doesn't belong to this, doesn't belong to this, doesn't belong to this, F doesn't belong to this, T doesn't belong to this. So together all the you know you can say that you have one member at least which doesn't belong to any of this, which doesn't belong to each class. So this set is functionally complete. All right. Okay. Now we are coming to the end of the class. Actually, uh, let me just. I think I'll have to.
Or
I'll have,
maybe in the lab we can initially discuss for 15
yeah,
minutes.
we'll have to, but unfortunately, I'm caught up in an interview during the lab hour.
Okay, then
So,
maybe I can discuss it.
yeah. So anyway, I'll just give an outline. Okay, I'll just give an outline. So what we shall show is that using. Okay, let me go back to this table. So for our discussion, further discussion, we will say that this F1, F2, F3, F4, F5, these are 5 representative functions. So F1 does not belong to T. So these are all, these are does not belong. So F2 doesn't belong to F. F3 doesn't belong to L. F4 doesn't belong to M. So these are functions which do not belong to the corresponding class. All right. So using these functions, so here this is the first construction. That is, you can define define complementation using F1, F2 and F3. So here actually the discussion is there, how to express using F1, F2 and F3. All right, how you can construct the complementation function using F1, F2, F3. Then we also show how you, because this T and F are also functions. You can't assume that, so these are, so you can construct this T and F using F1, F2, F3 and F. Basically, you construct one of the two constants using F, and then you use complementation, which is constructed using F1, F2, F3 to get the other one. All right. So here, as you can see, we'll just, and finally, we show that you can construct a 2 plus function. You can construct a 2 plus function with an odd number of t's using all of f1, f2, f5. Using all of these functions, you can construct. So in fact, we have constructed, functions g1 to g8, and these are, these turn out to be these functions, and all of these are actually, all of these can be used to construct functionally complete sets. So note that you have this your NOR, NAND, these are all coming from this construction. And so AND is by itself is not functionally complete, but you can use AND in conjunction with NOT. You have OR. So this is implication, okay? Implication, X implies Y. So this is equivalent to not X or Y, all right? So, and this is reverse implication. Reverse implication simply means X is implied by Y, all right? So this is X or not, sorry, X or not Y. So, and this is actually complement of reverse implication. So complement of reverse implication means you put this, and similarly this one you have, this is, all right. So this is the complementation. So all these functions, we see that we can compute from this. All right. So I could not, of course, difficult to do this in a semi-class. So I think we'll have to carry on with this in the lab. So we are giving you a lab assignment. Actually, construct, just to carry out this construction using given functions. All right. Okay, so we'll stop here now. Okay, thank you. Yeah. Okay.
So I had to ask something.
Yeah.